Okay, welcome to the course Fundamentals of Manufacturing Processes. And this week we'll talk about metal casting, third chapter. So we'll go through the basically casting defects and investment casting, shell mold casting, and some of the initial fundamentals of metal working. So this course is offered by Professor D.K. Dwivedi from Department of Mechanical and Industrial Engineering, IIT Roorkee, and I'm your TA Alka Jangid from IIT Kanpur. So firstly we'll go through some sample assignment questions which will help you in solving your weekly assignments. Then we'll go through some lecture notes. So okay, we'll begin now. Okay, so first question is method used for cleaning of fused sand particles on the casting surface is or are, and your options are chipping, sand casting, pneumatic hammer, or all of these. So for cleaning of the fused sand particles, all of these processes are used. So after casting, because of the high temperature of the your molten metal, some sand from the your mold, it gets attached to the casting. So that's why you require some cleaning processes. So these are some of the cleaning processes. So due to high temperature of molten metal, particles of molding sand, they get fused and adhered to the casting surface, and these are removed using tumbling, shot blasting, air blasting, centrifugal blasting, and hydroblasting. Here so the use of air is similar to pneumatic type of hammer, or centrifugal blasting, shot blasting, these are used for the steels as well. So these are some of the processes. Next question is fettling process is used for. Your options are cleaning of casting, pouring of molten metal, removing of gases from the mold, or removing of slag from the molten metal. So which one should be the answer? You can type it in chat box as well, and if you don't understand any question or anything, you can unmute yourself and ask. Okay, so in this question answer will be cleaning of casting. So fettling is one of the processes. Someone else has joined. Okay, so we are going through some sample assignment questions for you have joined late. So here first question was related to your cleaning of fused sand particles from the casting. So all these methods, they are used for this, and next question is also related to cleaning of casting. Someone else wants to join. Okay, so next, do you have any query? If you don't have any query, please mute yourself. Okay, so second question is, if you know the answer, you can type it in chat box as well, and if you don't understand the explanation, you can unmute yourself and ask. So fettling process is used for its cleaning for casting. Okay, so fettling is a metal finishing technique which removes excess material from the castings to create quality components. So you need some tolerance, finish, all this will be given by fettling. So it's often the first step in the finishing process for aluminum sand casting and gravity die casting, and this can involve removing unwanted elements. So it can remove unwanted elements. So this includes removing excess parts for pouring material into the mold, as well as irregularities caused by imperfections in the mold, and using various techniques such as, so this can include manual cutting, grinding, chipping, sawing, abrasive machining, and automated tools as well. Other finishing services such as these can include burning, arc care, shot blasting, heat treatment, and welding. So the level of finishing a casting requires and depends on the type of metal used and the end application. Next is based on casting defect. So red tells defect is formed due to, your options are gases, shrinkage, poor molding material, or pouring issues. So which one should be the answer? You can type it in chat box. So red tails will be the formation of some lines, irregular lines on your casting surface, okay, outer surface. So it looks like red tails, that's why it's called this. So the answer will be poor molding material. So one of the reasons for this defect is poor molding material. So the occurrence of the casting defect red tail can be attributed to the several factors related to mold material and the conditions during the casting process. The red tail defect in casting is characterized by a long thin line or ridge on the surface of the casting, and this defect occurs due to various issues related to the mold material and the conditions under which the casting is performed. So one of the reason can be soft ramming of the sand. So the sand in the mold must be properly compacted to ensure strength and resistance to thermal and mechanical stresses. And the soft ramming, inadequate compaction leads to insufficient strength, making the mold more susceptible to deformation and defects when subjected to the heat and pressure of the molten metal. Second is the continuous large flat surface on the mold. So the large flat surfaces in the mold can expand and contract unevenly when exposed to high temperatures, and this uneven expansion can induce your stress, leading to surface cracks and defects such as red tails. And the lack of geometrical features that can distribute the thermal stresses evenly makes large flat surfaces more prone to these issues. Excessive hardness of the mold. So an overly hard mold can resist thermal expansion when exposed to the heat of molten metal, and this resistance can cause the mold surface to crack and resulting in defects like red tails. And excessive hardness prevents the mold from accommodating the necessary expansion, leading to stress and cracking. Next question is, a defect caused by the poor molten metal quality is. Your options are blowhole, swell, slag inclusion, and cut. So swell, cut, blowhole, these all depends on entrapment of gases or the quality of mold material as well. So slag inclusion is the only one that depends on poor molten metal quality. So this one will be the answer. So slag inclusion is a casting defect which occurs when non-metallic materials or slag, it gets entrapped in a casting during the solidification process, and this slag can be a byproduct of the metal casting process and includes impurities. Slag inclusions can appear as pockets, ribbon-like entrainments, and also craters gas bubbles or as irregular appearances on the casting surface. Slag inclusions can be caused by several factors including molten metal flow, adding additives to the metal, oxidation during melting, and not removing slag particles from the molten metal before pouring, and also using contaminated casting materials. So while uh, melting your material, you sometimes use scraps. So in that scrap as well, there can be oxides already present. So those also can get inside your final casting. So this slag then reduces some of your mechanical properties. So it can reduce fatigue strength and other properties. Slag inclusions can negatively impact the quality of the casting in several ways, including surface. So in case of surface, slag inclusions can make the casting surface look worse and make it more difficult to machine. Interior, so slag inclusions can reduce the tensile strength of the casting and make it more likely to fracture. Overall quality, in this, slag inclusions can weaken the structure of the casting and reduce its overall quality. So to prevent slag inclusions, slag particles from the molten metal can be removed before pouring it into the mold cavity. Next question is, the most preferred process for casting cylinder head is? Your options are investment casting, centrifugal casting, shell mold casting, or all of these. So which one should be the answer? You can type it in chat box or you can unmute yourself and tell what should be the answer. Okay, so answer will be shell mold casting. Okay, so shell mold casting provides certain precision to the castings. So these are preferred over sand mold casting. So in this case, it is used for making cylinder heads and connecting rods. This is metal casting process similar to sand casting, and in that molten metal is poured into an expandable mold. However, in shell mold casting, the mold is a thin walled shell created from applying a sand resin mixture around a pattern, and the pattern, a metal piece in the shape of the desired part, is reused to form multiple shell molds. And a reusable pattern allows for higher production rates, while the disposable molds enable complex geometries to be cast. Shell mold casting requires the use of metal pattern, oven, sand resin mixture, dump box, and molten metal. This casting also allows the use of both ferrous and non-ferrous metals, most commonly using cast iron, carbon steel, alloy steel, SS, aluminum alloys, and copper alloys. And typical parts are small to medium in size, and these require very high accuracy, such as gear housings, cylinder heads, and connecting rods and lever arms. Next question is, in shell mold casting, shell mold is prepared by. So your options are silica sand, phenol formaldehyde, and magnesium oxide, grey sand, phenol formaldehyde and alcohol, silica sand and sodium silicate, silica sand and sodium silicate plus clay. So which one should be the answer? So first one will be the correct answer. So in case of shell mold casting, you require silica sand and some kind of binder. So binder acts as phenol formaldehyde. So these are the steps for shell mold casting. First, you have a two piece metal pattern which is created in the shape of a desired part, and typically from iron or steel, and other materials are sometimes used, such as aluminum or low volume production or graphite for casting reactive materials. Now first step is mold creation. So each pattern half is heated to 175 to 370 degrees Celsius, and it is coated with a lubricant to facilitate removal. Okay, and the heated pattern is clamped to a dump box which contains a mixture of fine silica sand and a thermosetting phenolic resin binder. Next you have mold assembly. So the two shell halves, so there is, you prepared it in half portion, so you connect these two and these are joined together and then securely clamped to form the complete shell mold, and if any cores are required they are inserted before closing the mold. The shell mold is then placed into a flask and supported by a backing material. Next you have pouring. So the mold is securely clamped together while molten metal is poured from a ladle into the gating system to fill the mold cavity. Cooling, and after the mold has been filled, the molten metal is allowed to cool and solidify into the shape of the final casting, and then you remove your casting from this mold. So after the molten metal has cooled, the mold can be broken and the casting is removed, and trimming and cleaning processes are required to remove any excess metal from the feed system and any sand remaining from the mold. Next question is based on investment casting. So it is used for, your options are carburetor housing, automobile piston, and engine crankshaft or impellers of turbocharger. So answer will be the impellers for the turbocharger. So investment casting is a process which can be used for making impellers for turbochargers in aircraft engines, and these are used in aircraft engines to help maintain performance at high altitudes. And the impellers in turbocharger, they pull the fresh air, compress it and deliver it to the engine. So as the impeller's speed increases, so does the air pressure. And the other options here, carburetor charging, carburetor housing, these castings are typically made using sand casting or die casting. And automobile piston, these are typically made using gravity die casting process, which involves pouring molten metal, molten aluminum alloy into a mold and then letting it cool and harden into shape. Last is engine crankshaft. It is manufactured by sand casting. Now next question is, in permanent mold casting, generally graphite mold is used for casting of. Your options are aluminum alloy, titanium alloy, tungsten alloy, and all of these. So in case of permanent mold casting, you have to remember that most of the elements, the metals and alloys that you use, they should be of lower melting point. So aluminum alloy here is the lowest melting point alloy out of these. So they should be the answer. Okay, so common casting metals are aluminum, magnesium and copper alloys. Some other materials can include tin, zinc and lead alloys. These also have very low melting temperatures. And also iron and steel are also can be cast in graphite molds. Typical products are components such as gears, wheels, gear housings, pipe fittings, fuel injection housings and automotive engine pistons. And the metal molds themselves are frequently called dies. And the coatings on the interior mold surfaces are applied to prevent adhesion and assist part removal. So for those who have joined late, we are going through some lecture assignment questions. Okay, so in this question you have to find out which metal will be the suitable for permanent mold casting. So for permanent mold casting, You choose metals and alloys which have low melting temperature. So in case of metal molds, you can only choose very low melting temperature these alloys, while in case of graphite mold you can go up to certain temperature. So castings on the interior mold surfaces are applied to prevent, there are coatings some applied so that there is removal is easier for this casting, they don't get adhered to them. Okay, so next question is, during cold metal working process of the metals, your options are elongated structure is developed, improves the mechanical properties, and there is porosity is collapsed, or all of these. So in case of cold metal working, which one will be correct? So in case of cold metal working, you don't have dynamic recrystallization, so elongated structure will be there, and there is also improvement of mechanical properties, and porosity is also collapsed. So all of these will be correct. So for imagining how this cold metal processing works, so for this you can remember this particular figure here. Okay, this one. So here this is cold rolling, here you have provided some granular structure, so here this has elongated, so metal about to pass between rollers and the grains that are distorted and elongated. Okay, so in case of cold working or cold forming, it is a metal working process which deforms metal below its recrystallization temperature. Okay, so in recrystallization temperature, what does it mean? So it is where your material starts showing recrystallization. So new crystals start to form at a particular temperature. So it is mainly between 0.3 to 0.4 times the melting temperature. Okay, so below that, if you perform your metal working processes, then those are called cold metal working processes. Okay, so in case of cold working, you are processing below recrystallization temperature and usually at room temperature. So while for some metals which have very low melting temperature, room temperature can also be hot working for them. For example, tin or similar metals to tin which have very low melting temperature, at room temperature, if you are providing some working, then it can be termed as hot working as well, or warm working. So the process can increase the strength of the metal and produce a good surface finish. Cold working is often used in industries like aerospace, automobile manufacturing, and medical devices. Some advantages of cold working include strengthens metal. So your strength of material as well as fatigue strength improves in case of cold working. So cold working can improve strength properties like fatigue strength and tensile strength because surface finish improves. And in case of fatigue strength, you mainly your crack always starts from the surface. So if you provide better surface finish, then it will have better better fatigue strength. Next is, it makes surface smoother. So cold working can produce a better surface finish than the hot working processes. In case of hot working, you can get some buckling on the surface as well as some oxidation of the surface. So that's why the surface finish won't be very good, economically efficient. So you don't have to provide some oven or some furnace to the system for heating that particular part. So cold working becomes cheaper compared to hot working. Cold working doesn't require heating and doesn't produce metal waste. And cold working processes can include rolling, drawing, tube reducing, forging, bending, shearing and squeezing. And for example, squaring shears can be used to slice or square sheet metal. Next question is, in the hot metal working processes of metals, your options are strain hardening is happened, the surface finish is reduced, grain structure is coarsened, or the limited deformation than the cold working processes. So which one should be the correct answer? So in case of hot working, other options are incorrect except the surface finish is reduced. So these are the comparison for hot working and cold working. In case of hot working, you perform metal working above recrystallization temperature. In case of cold, you perform it below. In case of this hot working, you have formation of new crystals, and in case of cold working, you have no formation of crystals. So for this, you sometimes require annealing as well. In case of hot working, surface finish is not good, while in cold working it is good. And there is no residual stresses in case of hot working, and in case of cold working there is formation of residual stresses. There is also less force is required because at high temperature your material becomes comparatively ductile, so you require lesser force, and in case of cold working you require more force. Next question is, the occurrence of casting defect red tail is possible because of, your options are soft ramming of sand, the continuous large flat surface on the mold, or the excessive hardness of the mold. So answer will be all of these. So the occurrence of the casting defect red tail can be attributed to the several factors related to the mold material and the conditions during the casting process. The red tail defect in casting is characterized by a long thin line or ridge on the surface of the casting, and the defect occurs due to the various issues related to the mold material and the conditions under which the casting is performed. So all these factors, soft ramming of sand, continuous large flat surface on the mold and excessive hardness of the mold, these are valid contributors to the occurrence of the red tail defects in castings. And there is proper compaction of sand, appropriate mold design to avoid large flat surfaces, and ensuring the mold material has adequate but not excessive hardness can help in preventing this defect. Okay, now we'll go through some lecture notes, or I'll just, for those who joined late, I'll go to initial questions once again. So first question was related to surface cleaning. So these are the various processes that I used for cleaning. So after casting, you have obtained the casting, but it is still connected to the riser part, runner part, and there is also some sand, fused sand that is there on the surface. So for that you require cleaning of the casting. So these are various processes. Next question was fettling process. It is also used for cleaning of casting. Next question was related to red tail. So we studied it again at the last as well. So this is related to poor molding material. So if there is compaction isn't sufficient in case of sand mold, so that can lead to formation of red tails. Next question was, a defect caused by poor molten metal quality is. So this one would be slag inclusion, because inclusion affects the your quality of the molten metal. So it can come from scrap as well, or from the sand as well, or your metal itself can react with the oxygen and can form some oxides which can act as inclusion. The most preferred process for casting cylinder head is shell mold casting. And shell mold casting, it is prepared by using silica sand, phenol formaldehyde as binder, and MgO. Investment casting is used. So impellers of turbocharger, they are made using investment casting. Other was permanent mold casting, so it is made using so aluminum alloys have lower melting point, so they can be easily made using permanent mold casting. For higher melting temperature ones, you go for sand casting. Now during cold metal working process of metal, so all these such as elongated structure, improvement of mechanical properties, and porosity is collapsed, all these are the advantages of cold metal working. In case of hot metal working, you have low surface finish. Strain hardening is happened. No, strain hardening is reduced in case of hot working due to high temperature. Grain structure is coarsened, so grain structure is also fine in case of hot working because of recrystallization. Limited deformation than cold working process. So deformation is also higher because of the improved ductility. Red tail. So all of these were the answer. Okay, so now we'll go through lecture notes. So first lecture is cleaning of casting. So after solidification of casting, mold is knocked out and solidified casting is taken out of the mold, and the solidified casting is attached with runner, riser, ingate, and some amount of sand which gets fused with the molten metal. So therefore cleaning of casting involves removal of gates, ingates, riser, feeder, etc. and surface cleaning, trimming, and finishing. So these are various steps. So first step is here removal of gates, ingates, riser, runner, and feeder. So there is not any diagram here, otherwise in previous lecture also you saw that there will be attachment of these risers and runners, so those need to be cut down and polished. Okay, so these can be removed by shocks, impact forces, and other process such as cut off the metallic part include bend saw, grinding machine, shearing machine, cutting torches, etc. So these all tools are required in case of your removal of gates, ingates, and runner riser. Next is surface cleaning. So due to high temperature of molten metal, particles of molding sand, they get diffused and adhere to the casting surface. So these are removed using tumbling, shot blasting, air blasting, centrifugal blasting, and hydroblasting. So for example, in case of shot blasting, you have some small okay, so in case of shot blasting, you have some shots of steel. So you have steel balls, you blast your steel surface with those balls, so it leads to finishing of this surface. So some extra material that is there, so that gets removed after heat treatment and it provides very smooth surface. So similar to those, there are various processes here which I used. Next is trimming. So it involves removal of fins, metallic chaplets, etc. and it is carried out using chisels and hammers or grinders, etc. So these are the some defects that are formed or some parts that are there, these are removed. Next is finishing. So in this stage It refers to final cleaning after removal of all unwanted metallic parts and sand particles. And depending upon the end product, it is carried out using machining, polishing, buffing, and chemical treatment. So for example, in case of if you have dipped your material in some acid, then some of the asperities that are there, some uh, some parts which are not uniform, they get dissolved first. So it can provide you with some surface finish. Next you have casting defects and their preventions. So firstly there is classification of casting defects. So first is molding related defects. So these are when there is mismatch. So if your cope and rack they don't match or they don't align properly, then these defects can arise. So first is flash, second is mismatch. So if cope and rack they don't match properly, then your castings halves won't match either. Next is filling related defects. So if your material cools very fast, then it might not reach to the places that are there. In some complex or edges or corners, they might not get filled properly. So these are cold shut, misruns, and blowholes, etc. Next is solidification related defects. So after solidification there is density difference. So it can give rise to the shrinkage cavity, porosity, etc. So porosity arises because the solubility of gases in molten metal is always higher compared to the solid metal. So at high temperature a lot of gases they get dissolved in the metal, and so when it starts solidifying from the outer wall, right? So inside there is still molten metal, so it will contain a lot of gases entrapped, so there will be a lot of porosity. Now first is molding related defects. So it will be due to improper closure across the parting line. So here because of this closure there is a lot of metal that get filled in the sand as well. So these need to be cut down, but this casting can be used. But in case of mismatch, your entire plane is shifted. Okay, so along parting plane, so this mismatch it can't be rectified. Next you have filling related defects. So first is incomplete filling. So cold shut, here it's shown here, misrun, these are incomplete filling, or they can be gaseous entrapments such as blowholes and gas porosity, and they can be related to solid inclusions as well. So sand inclusion, slag inclusion. Sand inclusion it will come from the mold, and slag inclusion it will come from molten metal. So these all reduce quality of your casting. Next we have solidification related defects. So solidification shrinkage such as cavity, porosity, centerline, sink, all these are related to solidification. Next we have hindered cooling, contraction. So hot tear, crack, distortion, all these can arise because of heat related problems. Now the definition of casting defects. So casting defects are imperfections or irregularities which compromise the quality specifications of a component, and there are various reasons and sources for casting imperfections, ranging from material failure to casting equipment or non-optimized procedures. Some of these defects may be tolerated or neglected, and some casting surface defects result in weak casting, odd shapes, and poor functionality. Therefore, they must be removed or prevented to ensure better functioning of the end product. So these are various types of casting defects, and but they are generally grouped into four categories. First is metallurgical defects. So these will depend on the material factor. Defects due to heat, so heat extraction, how it happens, that will be in this case. Mold material defects, so what type of mold material you are using. You can use metal, shell mold or sand mold. So all these materials, they will give rise to these defects. Next you have casting shape defects. So due to the shape of casting, so in this casting as well, you can see these are various defects which are known as casting defects. Now first is porosity defect. Okay, so it is based on metallurgical defect. So porosity defect, it is internal die casting defect which are usually difficult to spot. So these will be internally, it won't be shown on the. So for example, here as well, here you can see after polishing you reveal these type of defects. After, for example, you cut down it in the middle, or if you polish, then these gets then you can see these defects. So you will usually find them where there are small holes, voids or pockets of air on the metal. Typically porosities occur whenever air is trapped in the metal during the casting process. So as a result, gaps may occur at the top of the die, or the mold may fill too slowly. Thus, the resulting component may have weakened structural resistance. And there are two major porosity defects: gas porosity and shrink porosity. So first we are reading about gas porosity. So in this, when the cast metal solidifies inside the mold, it cannot retain as much gas as when it was in liquid form. Someone has joined. Okay, so gas porosity, when the cast metal solidifies inside the mold and it cannot retain as much gas as when it was in liquid form. Okay, so as I told earlier, the solubility of gases in molten metal is very higher compared to in solid form. So these gases, they remain soluble in the molten metal and the solidification starts from the walls. So that's why this gas remains trapped inside the metal. So therefore the metal tends to release gas. The inability of the gas to pass through the mold easily leads to the trapping of bubbles inside the metal, and these bubbles appear as pinholes, blowholes and penholes. Okay, so these are small holes that occur in the upper part of the die casted part, and you will usually see them by visual inspection in groups near the casting surface. Blowholes are larger holes that occur inside the cast workpiece. Unlike pinholes, they are not visible to the human eye. Therefore, they will need X-ray, ultrasonic, harmonic or magnetic analysis to detect them. Next you have penholes. So these are types of blowholes which appear on the surface of the workpiece, and they occur due to the air trapping when the metal is being poured into the mold, and these scars are shallow and they forms of the open holes. Okay, so it is open holes, not okay, it's not penholes, it's open holes. Next is, these defects appear round or oval on the surface of castings and they often have smooth surfaces. So how you um, if you have to separate between gas porosity and shrink porosity, then this is the, for gas porosity it will have round and oval appearance. Okay, so they often have smooth surface with bright yellow or bright white color. As a result, you can identify gas porosity defect in casting by visual inspection, and after the casting process, on the other hand, you need an X-ray device to check for this defect on non-machined surfaces. Now the causes. First is involved gases in metal alloy filling. So the metal casting involves filling dies with the molten metal alloy at high pressure and speed. Therefore, an inability of the molten alloy to flow stably and orderly may cause turbulence involving gases, and the turbulences often occur due to the blind areas in the gating system and unreasonable casting parameters and improper design of this gating system. Thus, you may notice some porosity defects due to the turbulences. Released hydrogen from the molten alloy. This is one of the main causes of porosity in casting. The moisture in air or smelting tools may enter the molten metal or steel alloy, thereby further decomposing into hydrogen. So, when cooling and solidifying the cast, the hydrogen solubility decreases, causing it to get released and form gas porosities. Gases from mold release agents. Now, upon contact, the molten metal alloy, it often heats up mold release agents, and as a result, they decompose and produce gas that ends up causing porosity defects. Likewise, using too many mold release agents, they can cause gas volatilization. Next, the remedies for these gas porosities. First, you have to ensure clean and dry metal alloy ingots which are used to prevent hydrogen formation. You have to use suitable casting parameters including injection speed and pressure. You have to control the smelting temperature to prevent overheating. You have to employ sprue and runner with a sufficient length of the greater than 50 mm. Thus, you will ensure a stable and adequate flow of gases. The mold release agent should be of the highest quality and controlled quality. Next, you have shrinkage porosity. So, as I told earlier, shrinkage porosity will look in irregular shapes compared to this circular or oval shapes in case of gas porosity. Okay, so shrinkage porosity is different from the round smooth surfaces of gas porosity, and these occur as jagged angular edges, and it is normal for metals to shrink and then cool and solidify. However, if the shrinkage cavity is uneven, distorts the shape of the component or creates internal holes, and it becomes a defect. The common shrinkage porosity defects are open shrinkage defects, closed shrinkage defects, and warping. So open shrinkage defects occur on the cast product surface as dips, caved surfaces or holes, and the air is drawn inside the mold when the metal alloy shrinks unevenly and will create an open shrinkage. In case of closed, they appear as holes inside the casting where there is uneven heating of the molten metal, and they occur in micro or macro forms. Macro shrinkages look like jagged lines or marks and are visible to the eyes. On the other hand, micro holes, they look angular and can be seen with microscopes. Warping defect, in this shrinkage, it occurs during or after metal solidification. and changing the component shape and dimensions. And these cause the metal to curve in flat or large sections. Causes, so high concentration of metal in specific areas of the mold, and there is too low injection pressure. So in case of sand casting, there is pressure is less compared to pressure die casting or other castings. Poor runner and gating system. So if design of the gating system is also not proper, then it may lead to the lower pressure and entrapment of gases, and also the shrinkage. So uneven pattern of metal solidification. So next is temperature differences in different parts of the molten metal. So the surface area also, if it is higher in one area of the part and different in other part, then it may lead to uneven cooling. Okay, so that may lead to shrinkage defect. Extremely high pouring temperature. Now remedies. So use of simple casting geometries with improved runner and gating design. So you can cast your casting in very simple geometry, and then afterwards you can provide some machining to it to get the final tolerances. So it may reduce the problem of such shrinkage defects. Ensure optimum filling of casting cavities by improving runner using simulation software. So you can provide the diameters of the runner, riser, all these ingates and all. So that may also lead to improvement in the uh, pressure of the gating design. Increase the metal injection pressure. So this pressure can also improve by using uh, some tools as well. Insert cooling coils, rips or internal chills. So these are also used for directional type of solidification. So this leads to control in the shrinkage. So shrinkage will mainly should be inside the riser. Okay, so it should be compensated by riser material. So for that we use a lot of these type of tools which can help you with the directional solidification. So these ensures proper heat dissipation. Next is clean the metal surface to remove contamination. Next is sinks. So a sink is a press down impact on the casting surface which does not precisely copy the mold design. So if the casting design is very complex, then it might lead to formation of sink. So sinks appear on the casting surface when there is a subsurface cavity present, and their depressions occur along thick walled areas on the metal surface. Since sinks they reflect light, you can easily identify these casting surface defects by visual inspection. For those who have joined late, we are going through some lecture assignment questions, some lecture notes. Firstly, we went through lecture assignment questions. Now, the causes of sinks. So, the uneven wall thickness of castings, they often lead to uneven shrinkage upon solidification. Partially overheated die, they can cause the casting to solidify slowly in those overheated areas. The inadequate venting of the die cavity, thereby causing gas to compress between the liquid metal surface and the cavity surface. Low injection pressure and poor feeding effects due to the short pressure holding time. Now, this can be prevented by using optimized optimization of the structural design of the casting to ensure even wall thickness. Or improvement in die cavities venting performance. Avoid overheating the die cavity and give the metal more pressure holding time, and increase the metal injection pressure. Next is slag inclusions. So here in picture also you can see these inclusions under microscope as well. They can be seen, then they will be seen in different color than the remaining casting. So they will be having different contrast. So a slag inclusion firmly attaches to the casting, reducing the mechanical characteristics of the final product, and it usually occurs when non-metallic materials, they cause irregular crusts on the casting surface, and the casting defect is a ribbon-like entrainment or pocket with sharp edges and regular shapes. And in addition, other forms of inclusions include sand, nails, dirt or oxides. So although they are only a few millimeters thick, you can see them with your eyes. Now the causes. So pouring and solidification of liquid metal containing slag particles. So your material, pouring material, already it might have this slag particles. Improper gating system, so it can come from your sand mold as well. And formation of insoluble intermetallic compounds during the solidification process, thus causing them to segregate in residual liquid. So the liquid that will solidify at last, it might have higher quantity of these intermetallic systems. Adding alloy that has not fully dissolved in the melt. And now this can be prevented by using thorough and regular die cleaning. Improve the design of the gating system and use clean molten metal. And we can also apply a small piece of alloy material and observe metal alloy as they change. So for understanding whether it will form intermetallics or not, you can use a small piece of alloy material and firstly observe whether it will form the metal alloy as it changes. Next is dross. So it refers to a metal loss which occurs during non-ferrous metal casting operations, and as metal melts, it oxidizes to form layers of the impurities and scum which floats to the surface of the metal. And the impurities, they occur due to the mixing of the oxide of the base metal and the other metals on the surface. Cause is thermite reaction. So thermite reaction is one of the reaction that is related to aluminum. So that reaction can also create dross. Too high metal temperature and formation of oxides. So at high temperature, material also reacts highly with the oxygen and other air, so it might lead to formation of dross. So formation of oxides due to reactions which occurs between the air in the mold and the high temperature liquid metal. So it can be avoided or prevented using these particular remedies. So firstly, avoid stirring, which may result in oxidation and thermite reaction. And also reduction in metal temperature. So pouring temperature should be kept less, not very high. Decrease the melting time. So for the higher time you keep your metal in molten state, it will have more time to react with air and it will form more amount of oxides. Next is soldering. So it is a common casting defect during the casting process, and it occurs when molten metal attaches itself to the surface of the die cavity and stays there after removing the casting. So for this you can provide some lubricant or some coating to the die so that your casting deattaches from the die very easily. Now consequently, some areas of the casting parts are either missing material or have excess material from the die. So you can identify soldering by visual inspection. So these are the various causes of soldering. First is damages, insufficient hardness or low roughness of the die cavity. Next is improper injection mechanism causing inclined injection. And then you have overheating the molten metal alloy or dies, or using mold release agents with poor quality, and also insufficient amount of iron element in alloy. Now these can be prevented by repairing any damage to the die cavity and improve its roughness. So if roughness will be higher, then detachment will be easier in ejection of the casting. Now adjust draft angles and gate design. So some allowances can also help with the easier removal of the casting from the die cavity. So die cavity, if it's made of metal and other and graphite, then uh, it can cause this soldering defect. So the remedies can be repair any damage to the die cavity and improve its roughness, adjust draft angles and gate design, ensure balanced ejection by optimizing the ejection mechanism, monitor and control the temperatures of die and molten alloy, use of high quality mold release agents, and also use an adequate iron element with 0.8% to 1.1% margin. Next is defects due to heat. So first is hot tears. So there are 5 casting defects caused by heat, including hot tears, cold shut and thermal fatigue. First is hot tears. So in this case, these are some of the significant casting abnormalities that occur due to the heat, and this defect occurs during the solidification of the metal casting, and at this stage thermally induced tensile strains and stresses they develop in the metal, and the hot tear occurs as the metal contracts when solidifying, and you typically see them as irregular or linear patterns on the die casted parts. Now causes is thermal contraction of the metal surface, inadequate metal pouring temperature, and improper solidification process and placement of gates. So these are some reasons, and remedies can be use of good fillet at junctions, place the gates near the die accurately, and employ standard solidification methods, and ensure even thickness throughout the material. Cold shut as shown here. So here in this case, these defects are cracks which have round edges, and these occur when metal flows into the mold from more than one point. However, the metal is too cold and cannot merge properly, to form a perfect piece. Thus, a cold shut occurs as cracks with rounded edges through the middle of the workpiece, and it creates a weak spot on the casting. So, for example, if you are using this product in some machine component, then this might fail from this part, so it creates a weak spot. Causes are improper design of the gating system and low temperature of liquid metal. So pouring temperature, if it's lower, then these cold shards they can form. Reduced fluidity of molten metal. So fluidity also should be good, so it can flow in the complex regions as well. Thin sections of the casting, this can also be one of the reasons. So remedies, so it optimizes the gating system to prevent narrow cross paths and ensure proper metal flow. Improve gas permeability of mold. So if permeability is not good, then also it can arise. So permeability should be appropriate. Next is increase the metal pouring temperature to prevent early solidification. Next question is thermal fatigue. So the defect is prevalent in aluminum die casting because the dies they undergo high thermal stress, and the thermal stress develop from the thermal gradients which occur during the heating and cooling of the surface during ejection and lubricant spraying. Since injection, ejection and lubricant spraying, since die casting dies are prone to high thermal and mechanical loads, thus subjecting them to repeated cycles of very low and high temperatures will lead to structural weakness and the cracks within the component. Now the causes of thermal fatigue is continuous subjecting the die to high temperature, edges and corners with the too small radius, and also the temperature gradient is too close to the gate. Now this can be prevented by giving corner and edges permissible radius and reduce the temperature gradient close to the gate, and also allowing the die to cool for some period. Now these are related to mold material casting. Okay, so there are 7 types of casting defects caused by unsuitable mold material. First is cuts and washes. So as we can see here, some material will go outside the cavity, so it will penetrate inside the sand. So it will be because of the mold material. So these are areas of excess metals which occur when the molten metal washes away and part of the molding sand. When this happens, the sand does not have enough strength to resist erosion, and cuts and washes they appear as low bulges along the surface of the workpiece, and they usually tilt towards the end where the liquid metal had more pouring pressure. Causes excess metal in some areas of the mold, and the high velocity flowing of molten metal causes excess metal to pass through the gate. So remedies, so ensure proper design of the gating system and improve the core and mold strength, and also addition of more binders to the core set. Next is fusion. So fusion in another sand casting defect which occurs when the sand grains they fuse with the flowing liquid metal, and this results in a thin layer of hard, glassy, crusty, firmly attached to the casting. And the main cause of this defect is the low refractoriness of sand. So, as a result of the sand's low refractoriness, it is unable to resist the high temperature of the liquid metal, thus a fusion defect occurs. So, causes: low refractoriness of sand or clay, mixing metal with sand grains, and too high metal pouring temperature. Remedies: so it enhances the refractoriness of the molding material. So if you choose a sand in such way, or the mixture of sand in such way, that it should have good refractoriness, and reduce the pouring temperature of molten metal. Next is runout. So runouts happen when the molten metal leaks from the mold. So as a result of this, the mold cavity will not be filled completely. Therefore, you tend to get missing or incomplete casted components. In most cases, the appearance is smooth, but you can also get irregular and rough runouts sometimes. So here, as it's shown here, so a faulty mold or die casting machine. And remedies: so you can prevent this by designing casting molds with precision, and also inspect mold before casting and replace defective ones. Use high quality raw materials that can withstand high temperature for designing molds. Next is swells. So this occurs due to metallostatic forces, which causes the mold wall to move back, causing a swell in the dimensions of the workpiece. This means that the casting will enlarge beyond the desired volume, showing as slight smooth bulges. As a result, its feeding and machining requirements will increase, and it may lead to metal wastage. Now the causes: low strength mold, improper ramming of the sand mold. Remedies: you have to design molds to withstand molten metal pressure to prevent the mold wall from moving backwards. Also, use of stronger and well rammed molds. Next is drops. So these defects happen when casting is still in molten form, and they are caused when the pieces of loose molding sand or lumps, they drop from the surface of the cope into the mold cavity. As a result, an abnormal and irregularly shaped projections occurs on the casting surface. Drops can also make the metal surface look dirty and unsuitable for use. The causes: so low sand strength and insufficient fluxing of the molten metal, soft ramming, and absence of reinforcement of sand projection in the cope. Remedies: so we can use sand with higher strength, removing the molten metal impurities with proper fluxing, providing harder ramming, and reinforce the sand projections with the nails. Next is metal penetration. So this occurs in situations when the molten metal penetrates openings or gaps in the molding sand, and the main reason for this is to grain size of the molding sand is too coarse, preventing the proper flowing of the liquid metal. Consequently, you will get a rough and irregular casting surface, which lowers its aesthetics, and you can easily see the effects of metal penetration with your eyes. The causes is using sand with very high permeability and low strength, soft ramming of sand, using coarse and large sand grains. It causes more extreme metal penetration. Lack of mold wash. Remedies, so use small sized and high strength grains. Ensure proper ramming and also low permeability of sand. Now this is how red tails will look like. These will be irregular lines on the surface of casting. So red tails, they appear as irregular cracks or lines on castings, and these defects, they occur due to the compression failure on the mold cavity surface when the molten metal is excessively hot, and the molten sand, it expands under the influence of heat, which causes the mold wall to move backwards and give way. In the process, the casting surface will show a small line mark, and if such failure occurs severely during the casting procedure, you may notice some small lines on the component surface. The causes are poor expansion capabilities of sand, improper mold design, excessive metal pouring temperature, and it can be prevented by adding combustible additives to molding sand, reduce the metal pouring temperature, and also designing mold to be less hard to ensure adequate expansion. Now there are two defects which are related to casting shape. So improper casting shape can also cause two types of defects, mismatches and flash. So first is mismatches. So in this case, this is casting defects which occur due to the misalignment of the lower and upper parts of the mold, and it could occur when the cope and drag of the mold are not properly lined up before pouring the metal. And there are two types of mismatches, namely mold shift and core shift. And mold shift is a result of the misalignment of mold, and it is often shows as a horizontal displacement. On the other hand, core shift occurs due to misalignment of the core, and it appears as a vertical displacement. So the causes can be loose box pins, wrong pattern pins, and placing of the upper part and lower part of the mold wrongly, which can cause misalignment. Now it can be prevented by ensuring proper mesh plate pattern alignment and mounting. Use the right molding box closing pins. Next is flash. So flashes are any excess or unwanted material which occurs as thin, irregular shaped occurrences on the parting line of the die casting. Typically, it is a thin sheet of metal forming on the parting faces and turning into troughs after remelting. So since flashes, they often have larger size, they can be seen by visual inspection. Causes is insufficient clamping force, inadequate cleaning of the parting surface, and too high injection speed and filling temperature, insufficient strength of the die material, and deformed or worn out hinges of the casting machine. Now it can be prevented by adjusting the casting parameters such as injection speed, filling temperature, and clamping force, ensuring regular maintenance of casting machines, and also clean up the die cavity and parting surface. Now lecture 23. So in this, firstly shell mold casting is told. Okay, so shell mold casting is an expandable casting process which uses resin covered sand for making the mold, and a reusable pattern allows for higher production rate while the disposable molds they enable complex geometries of cast. And as compared to sand mold casting, this process has better dimensional accuracy, high production rate, and lower labor requirement. So this is the process. There are only 3 steps. First you have to make shell, then shell mold casting, then removal and cleaning of casting. So for this you require these various tools: drop box, sand resin mixture, this heated pattern, and this shell. These all are required. So this pattern is heated, and because of that this binder sand, it gets deposited on this part. Okay, so there is a layer that is created, and after that there are two halves that are connected, and then it is there is molten metal is poured inside it, and it is left for solidification. After solidification there is ejection of this part, and there is finished casting. So this is the baking material, this is inside is the casting, and this is the shell mold. So this shell mold casting, it will be providing you better accuracy compared to sand mold because of the higher hardness and strength of this shell mold compared to your sand mold. Next you have investment casting and permanent mold casting. So in investment casting you have wax pattern first. So first, often referred as lost wax casting, as melted wax pattern is melted out of the mold after it has been formed. So firstly you prepare this wax mold. Okay, so then you assemble various parts, then this is dipped inside the ceramic slurry. Okay, so this ceramic slurry will form various layers, and then finally this wax will be evaporated or burnt out. Okay, so this is known as de-wax or burnout. Okay, so after this there is cavity ready. So this cavity is filled with molten metal. Okay, so gravity pouring, then after that you remove this ceramic this outside layer that you formed, that is removed. Then you cut off these metal parts that you have formed, you remove, and you finish this casting. Okay, so knockout, cut off, finished casting, these are various steps. Now the advantages of the investment casting. So firstly it will give very smooth surface with no parting line, and it also has dimensional accuracy, and there is, so compared to, yeah, do you have any query? If not, then please mute yourself. Okay, so compared to sand mold casting, it provides better surface finish. So there is also no parting line. So this entire thing is made in one part. So there is no parting line as well, and there is dimensional accuracy is also good, and there is certain unmachinable parts which can be cast and into pre-planned shapes. So some of the disadvantages are that it is expensive process, and it is limited to small size castings, and it presents some difficulties where codes are involved. So if you want to make hollow shapes, then it becomes very tricky. Now very long production cycle time than other casting processes, and also infeasible for high volume manufacturing due to high cost and long cycle time. Applications, so in aerospace and power generation industries to produce turbine blades with complex shapes and cooling systems. Next is permanent mold casting. So permanent, in case of sand mold casting, it is your mold that you have formed, it is destroyed afterwards. So that's why it's temporarily kind of mold. So in this case your mold will be used multiple times. Okay, so that's why it is called permanent mold. So permanent can be graphite mold, it can be metal mold. So it is often used for high volume production of simple geometry parts which are made up of non-ferrous metals such as aluminum alloy, magnesium alloy and copper alloys. Here in figure also you can see there will be some. Okay, so there is gating system, entire gating system, sprue, runner, mold half and all, and there will be a mold cavity. Next, the advantages. So it provides better mechanical properties. Why? So in this case you have molds which have better thermal conductivity. Okay, so as soon as you pour material, there will be heat transfer will be higher, so there is less chances of shrinkage and gas porosity formation, and also there will be grain structure will be more equiaxed compared to uh, elongated type of structure or uh, some other type of structures which will form in case of dendritic type of structure in case of sand casting. So it will also have homogeneous grain structure and chemical composition, and it also has good surface quality. It has low dimensional tolerances, and also it has little scrap process, so formation of scrap is less compared to sand mold casting. Okay, and because of use of these graphite and metal molds, surface finish will also be better, because in case of sand mold casting your sand also gets stuck to the casting surface and it can get displaced as well, making the surface quality very worse. Disadvantages. Now it has high cost of molds and their limitation in casting of high melting point metals into metallic molds. Okay, so metal mold can only go up to the melting temperature of that particular metal that you have used for making mold. Okay, so very not even up to melting temperature, you have to keep it below below that temperature. So intrinsic and complex shapes cannot be cast, and also large parts cannot be cast, and there, because the cost of that mold will become very high. Next we have metal working processes and hot and cold working. So first we have hot working. So it refers to process where metals are deformed above their recrystallization temperature. So as I told earlier, recrystallization temperature means where formation of new crystallites will be starting. So around 0.3 to 0.4 times the melting temperature of the metal, your material will start showing formation of new crystals, stress free crystals, if it has some residual stresses already in the material. So if you deform your material, then it has some activation energy for the formation of those new grains. Okay, and the strain hardening does not occur in this case. In hot working, strain hardening does not occur because dislocations don't get multiplied that much, because it keeps getting reduced as well because of the dynamic crystallization. And at elevated temperatures, metal weaken and become more ductile. So because of the higher ductility also, the deformation of materials become easier at temperature above crystallization temperature, so there is less amount of force is required compared to cold working, and also the rolls that are used, they will also deform less. Now rolling, forging, extrusion, hot drawing, piercing, these are some of the typical examples of processes which can be carried out above recrystallization temperature. The advantages, so requirement of low working forces, this is one of the advantage, okay, because your material is ductile in nature, therefore general purpose machines can be utilized. Also it can break up large crystals and produce favorable alignment of elongated crystals, and it can also remove defects of as cast metals like gas pockets, voids, etc. So in case of, for example, hot rolling, you're squeezing material to the lower thickness, so if there is some porosity present, it gets compressed, so it will be having a material which will be much denser compared to the casted one, as cast one. The disadvantages, it has poor surface finish because of high temperature processing, and there will be poor dimensional tolerances, and there is formation of scales, oxides on the surface of the workpiece. So at higher temperature, material has higher tendency to form oxides. Next is cold working. So it refers to the process where metals are deformed below their recrystallization temperature and the strain hardening occurs. So if you're performing metal working process below 0.3 times the melting temperature of metal, so basically mainly at room temperatures, then it won't undergo any recrystallization, so it will get strain hardened, your material gets strain hardened. So rolling, forging, extrusion, cold working, piercing, these are some of the typical examples of processes which can be carried out below recrystallization temperature. Now these are the advantages of cold working. So first is there is no heating requirement. So for example, in case of hot working, you require the heating chamber as well. So some oven or furnace is required for your material to get heated. So that adds to the cost of the entire process. So the entire tool becomes very costly compared to cold rolling. Now better surface finish and superior dimensional control are achieved. Strength, fatigue and wear properties are also improved. So as the surface finish becomes better, so you know that in case of fatigue, as I told earlier, cracks start from the surface. So if surface finish is very good, then it will show better fatigue properties as well. And in case of cold working, what you're providing dislocation multiplication and an elongated type of structure. So it will have directional properties as well. So there will be, for I think it's shown here. So here this is the cold work material here. So in one direction you will be having different strength compared to in this direction. Okay, so that's why in case of cold materials you will be having better strength as well because of this type of structure and because of higher density of dislocations. And wear properties are related to hardness as well. So as I told earlier, dislocation density will affect these properties. The disadvantages, so in case of cold working, you have heavier forces are required. So your material won't be ductile as in case of hot working. So in cold working, you'll require higher forces for getting the same amount of thickness reduction. Strain hardening occurs and it may require intermediate annealing treatment to relieve internal stresses. Okay, so strain hardening occurs because you are not providing any high temperature for dislocations to get annihilated. Residual stresses may be produced. And also for cold working, the ductility and the yield point stress of the steel are important. So you must know these properties of the steel before starting to cold work. Typical example of processes. So these are some of the schematics for cold working and hot working. So in case of rolling, so this is cold rolling, this is hot rolling. In case of hot rolling, this rolls, this is metal that is being reduced in the thickness. So after squeezing, this thickness becomes reduced compared to initial thickness. Okay, so here this material is heated, and because of that it will have higher ductility and it will show higher thickness reduction. And in case of cold rolling, and here it's forging. So in case of forging, there is hammering that is done after putting material through the die. In case of extrusion, this will be, in this case your material will be in semi-solidus form and this will be squeezed through the one of the opening, and this will provide you products with uniform cross section. So very complex shapes can't be made using extrusion. Next is effect of rolling on microstructure. So cold rolling shows elongated grain boundary microstructure due to very high deformation and dislocation multiplication, which also makes it anisotropic. So in cold rolling you can see your grains are elongated. So in one direction you have different grain size, in other direction you have different grain size. So strength, elastic modulus, optical properties, all these will be different in different directions. So that's why it will be anisotropic. In case of hot rolling, dynamic recrystallization occurs. So equiaxed type of grains, they will form. Okay, so that's why these materials are isotropic. So this will have isotropic properties. Okay, so notes are completed. So I'll go through questions, sample assignment questions one more. So if you want to leave the meeting, you can leave. I'll go through the sample assignment questions once for those who joined late. Okay, so first question was method used for cleaning of fused sand particles on the casting surface is R. And your options were chipping, sandblasting, pneumatic hammer, and all of these. So the answer was all of these. Okay, so here surface cleaning is due to high temperature of molten metal and particles of the molding sand. They get fused and they adhere to the casting surface, and these are removed using tumbling, shot blasting, air blasting, centrifugal blasting, hydroblasting. Next question was fettling process is used for. Your options are cleaning of casting, pouring of molten metal, removing of gases from mold, or removing of slag from the molten metal. Answer will be cleaning of casting. So fettling is a metal finishing technique which removes excess material from castings to create quality components, and it's often the first step in the finishing process for aluminum sand casting and gravity die casting. Now fettling can involve removing unwanted elements, which includes removing excess parts of for the pouring material into the mold, as well as irregularities caused by imperfections in the mold. Using various techniques, these can include manual cutting, grinding, chipping, sewing, abrasive machining, and automated tools. Then other finishing services, these can include burning, arc care, shot blasting, heat treatment, and welding. The level of finishing a casting it requires depending on the type of metal used and the end application. Next is red tail defect is formed due to. Your options are gas, shrinkage, poor molding material, and yeah, correct. Okay, so the in case of red tails, they are formed due to the displacement of the mold material. So if ramming of the sand is soft, then this sand may get displaced and there might be some formation of uh, some irregular lines which look like red tails. Okay, so the occurrence of the casting defect red tail can be attributed to several factors related to mold material and the conditions during the casting process. And the red tail defect in casting is characterized by a long thin line or ridge on the surface of the casting, and this defect occurs due to various issues related to the mold material and the conditions under which the casting is performed. First is soft ramming of sand, when the sand and mold must be properly compacted to ensure strength and resistance to thermal and mechanical stresses. The soft ramming or inadequate compaction leads to insufficient strength, making the mold more susceptible to deformation and defects when the subjected to the heat and pressure of the molten metal. Continuous large flat surface on the mold. Large flat surface in the mold can expand and contract evenly when exposed to the high temperatures, and this uneven expansion can induce stress leading to surface cracks and defects such as red tails, and the lack of geometrical features that can distribute the thermal stresses evenly, which makes large flat surfaces more prone to these issues. Next is excessive hardness of the mold. So an overly hard mold can resist thermal expansion when exposed to the heat of molten metal, and this resistance can cause the mold surface to crack, resulting in defects like red tails. Excessive hardness prevents the mold from accommodating the necessary expansion, leading to stress and cracking. Next question is, a defect caused by poor molten metal quality is. Your options are blowhole, swell, slag inclusion, and cut. So try to answer this one as well. So which one should be the correct answer? So only slag inclusion is the one that is purely because of the poor molten metal quality. So slag inclusion is casting defect which occurs when non-metallic materials or slag they gets entrapped in a casting during the solidification process, and the slag can be byproduct of the metal casting process and it includes impurities. Slag inclusions can appear as pockets, ribbon-like entrainments, craters, gas bubbles, or an irregular appearance on the casting surface. Slag inclusions can be caused by several factors including molten metal flow, adding additives to the metal, oxidation during melting, not removing slag particles from the molten metal before pouring, and using contaminated casting materials. Slag inclusions can negatively impact the quality of casting in several ways. including slag inclusions can make the casting surface look worse and make it more difficult to machine. These can also reduce the tensile strength of the casting and make it more likely to fracture, and these can also weaken the structure of the casting and reduce its overall quality. And also, to prevent slag inclusion, slag particles from the molten metal can be removed before pouring it into mold cavity. Next question is, the most preferred process for casting cylinder head is? So your options are investment casting, centrifugal casting, shell mold casting, and all of these. So I would suggest you should remember some of the applications which can be asked in questions or in exam. Okay, so you should remember at least main applications of these casting methods. So here answer will be shell mold casting. Okay, so this casting is used for making cylinder heads and connecting rods. And this shell mold casting is metal casting process similar to sand casting, in that molten metal is poured into an expandable mold. However, in shell mold casting, the mold is a thin walled shell created from applying a sand resin mixture around a pattern. And this pattern, a metal piece in the shape of the desired part, is reused to form multiple shell molds, and a reusable pattern allows for the higher production rates, while the disposable molds they enable complex geometries to be cast. Shell mold casting requires the use of metal pattern, oven, sand resin mixture, dump box, and molten metal. Shell mold casting allows the use of both ferrous and non-ferrous metals, most commonly using cast iron, carbon steel, alloy steel, stainless steel, aluminum alloy, and copper alloys. And typical parts are small to medium in size and require high accuracy, such as gear housings, cylinder heads, connecting rods, and lever arms. Next question is, in shell mold casting, shell mold is prepared by, your options are silica sand, phenol formaldehyde plus MgO, grey sand, phenol formaldehyde alcohol, silica sand, sodium silicate, silica sand, sodium silicate plus clay. Answer will be first. So here two-piece metal pattern is created in the shape of the desired part, typically from iron or steel. Other materials are sometimes used, such as aluminum for low volume production or graphite for casting reactive materials. Next step is mold creation, in which each pattern half is heated to 175 to 370 degrees C, and it is coated with the lubricant to facilitate removal, and the heated pattern is clamped to a dump box which contains a mixture of fine silica sand and a thermosetting phenolic resin binder. Next is mold assembly. In this, the two shell halves, they are joined together and securely clamped to form and compensate the shell mold. If any coats are required, they are inserted before closing the mold. The shell mold is then placed into a flask and supported by a backing material, and then after pouring, so the mold is securely clamped together while molten material is poured from a ladle into the gating system to fill the mold cavity, and then after that cooling. So after the mold has been filled, the molten metal is allowed to cool and solidify into the shape of the final casting. And after that you have casting removal. After the molten metal has cooled, the mold can be broken and the casting is removed. And trimming and cleaning processes are also required to remove any excess metal from the feed system and any sand remaining from the mold. Next question is investment casting is used for. Your options are carburetor housing, automobile piston, engine crankshaft, impellers of turbocharger. So answer will be impellers of turbocharger. So investment casting is used to make these in aircraft engines, and these are used in aircraft engine to help maintain performance at high altitudes. And the impellers in turbochargers pull the fresh air, compress it, and then deliver it to the engine. And as the impeller's speed increases, so does the air pressure. Carburetor castings are typically made using sand casting or die casting. Automobile pistons are typically made using a gravity die casting process, which involves pouring molten aluminum alloy into a mold and letting it cool and harden into shape. Next is engine crankshafts. They are manufactured by sand casting. Next question is, in permanent mold casting, generally graphite mold is used for casting of. Options are aluminum alloys, titanium, tungsten, and all of these. So answer will be aluminum alloys. So common casting metals are aluminum, magnesium, copper alloys, tin, zinc, and lead alloys, and also iron, steel, which can also be cast in graphite molds. Typical products are components such as gears, wheels, gear houses, fuel injection housings, and automotive engine pistons, and the metal molds themselves are frequently called dies, and the coating on the interior mold surfaces are applied to prevent adhesion and assist part removal. Next question is, during cold metal working process of metals, which option will be correct? So here elongated structure is developed, improves the mechanical properties, and porosity is collapsed, or all of these. So answer will be all of these. So here you can see, after rolling, the grain structure changes from equiax to elongated. So cold working or cold forming is metal working process which deforms metal below its recrystallization temperature, usually at room temperature, and the process can increase the strength of the metal and produce a good surface finish. Cold working is often used in industries like aerospace, automobile manufacturing, and medical devices. And some advantages of cold working include strengthening of metal. In case of cold working, it can improve strength properties like fatigue strength and tensile strength, makes surface smoother. So cold working can produce a better surface finish than hot working, and economically efficient. Cold working doesn't require heating and doesn't produce metal waste. Cold working processes can include rolling, drawing, tube reducing, forging, bending, shearing, and squeezing. Next question is, in hot working process of metals, strain hardening is happened, the surface finish is reduced, grain structure is caused, and limited deformation than cold working processes. So answer will be second, because other processes are incorrect. So in case of hot working, you don't see much strain hardening because there is annihilation of dislocations at high temperature, and also grain structure is get reduced because of dynamic recrystallization. Limited deformation, so deformation is also higher compared to cold working because your material becomes more ductile compared to in cold conditions. And these are the comparisons given as well. So for example, in hot working, your material is above recrystallization temperature, and in case of cold working, it's below recrystallization temperature. In case of hot working, you have formation of new crystals. In cold working, there is no formation of crystals, so it is deformed grains, elongated grains. In hot working, surface finish is not good, and in cold working it is better, so better tolerance as well. No residual stresses. In case of cold working, you have residual stresses as well. In case of hot working, there is less force is required because of high ductility. In case of cold working, more force is required. Next question is the occurrence of casting defect red tail is possible because of. Options are soft ramming of sand, the continuous large flat surface on the mold, the excessive hardness of the mold, or all of these. So answer will be all of these. So the occurrence of the casting defect red tail can be attributed to several factors related to mold material and the conditions during the casting process. This defect in casting is characterized by long thin line and ridge on the surface of the casting, and this defect occurs due to various issues related to the mold material and conditions under which the casting is performed. So all three factors, soft ramming of sand and continuous large flat surface on the mold and excessive hardness of mold, are valid contributors to the occurrence of the red tail defects in castings. And the proper compaction of sand, appropriate mold design to avoid larger flat surfaces, and ensuring the mold material has adequate but not excessive hardness can help in preventing this defect. Now after that, we went through the lecture notes. First was cleaning of castings, then casting defects and their preventions, then shell mold casting, then through investment and permanent mold casting, then metal working processes, which is hot and cold working processes.